Welcome to Radio System Design, Module 11, Nonlinearity, Harmonic Distortion, and Spectral Growth. We're just going to talk briefly about the ideas of harmonic distortion and spectral growth from a qualitative standpoint, because in the previous lecture and in the future lecture on intermodulation, we'll actually do some detailed calculations. So what is harmonic distortion? The outputs of a nonlinear system, as we've seen, contain signals that are harmonics or integers of the input frequency. A DC level at the output results when one of the Taylor series coefficients has an even J. Even order harmonics happen also when we have an even J, and odd order harmonics happen when we have an odd J. So that means alpha 1, 3, 5 will give us odd harmonics, and the even harmonics will happen from 2, 4, 6. The amplitude of the nth harmonic grows in proportion to the input voltage to the nth power. And so this is kind of important. If we look at our system where we've got x equals a n cosine omega t, once again we're back in the voltage domain because we're dealing with the voltages in the Taylor expansion of the linear gain. And you can see that the coefficient in front of the first fundamental goes with a, and the nth harmonic, the second one, goes with a squared, and the third harmonic goes with a cubed. Now, this doesn't mean that these three coefficients, I'm sorry, let me write it this way. Change my pen color, I think this will be a little bit easier to see. What it doesn't mean is that this is smaller than this or is smaller than this. You need to realize that likely this is smaller than the fundamental and this one is smaller than the second harmonic. And the reason is you need to remember there's an A3, A2 precursors for this, or prefactors for this. So, but what we notice is the trend. So as the input increases, I'll go back to my red pen here, as the input increases, these harmonics grow at a faster rate. So I'm just going to write that down. Harmonics increase faster than fundamentals. As input increases. This is really important because it's basically saying if you have a nonlinear system, when the signal's small, you may have very little harmonics. But as you increase the signal, the ratio of the harmonics to the fundamental is going to increase because the harmonics increase faster. So let's look at an example. If we have a transmitter from a 900 megahertz GSM cell phone, it generates harmonics of 900 gigahertz. Explain what might be the effects of these harmonics. And you're probably thinking, okay, I'm going to generate 900, 1.8 gigahertz, and so forth. But if you actually plot this out, it turns out that the second and the sixth harmonic land right on top of other communication bands. So this becomes a real problem when your harmonics are disturbing an adjacent band. And you may say, well, I'm just going to use a filter. But remember, if I were to come in with a filter, let's just say, this is a cartoon. If I come in with a filter that lets this through, I've got some roll-off, right? So even out at the sixth harmonic, I'm still passing a little bit. It is attenuated, but I still get a little bit through. So the only way to really fight this is to get a very good filter or to try to eliminate those harmonics. So this particularly is a problem when you try to transmit high output power and you get a lot of harmonics, that the harmonics at these, even though they might be filtered a little bit, are still significant. So we really have the problem of not only we're generating the harmonics, but that they increase faster than our input power does because of the fact that the voltage increases by a to the n, where nth is the n harmonic. All right, so let's talk a little bit about spectral growth. The first part was about harmonic distortion. But there's another way that we can generate harmonics, and this is what happens if we have a nonlinear system, we pass it through a nonlinear transmitter. Now, mathematically, we've done this in the past where we've had the Taylor series, but this is sort of qualitative. Let's imagine we're going to pass this through this amplifier, and it's got a limiter on it, meaning it can't go any higher. What's going to happen is that the low amplitudes are unchanged, but the higher amplitudes are distorted. So if you look at the frequency domain, we might have a nice pulse shape here, but after it comes out, we've actually have extra frequency component, and that is the spectral growth because of the nonlinear operation of the amplifier. Before, when we looked at a single frequency, it was easier to follow it, but if you've got a broadband signal coming in, qualitatively, we're just going to have an expansion of that signal as it goes through a nonlinear system. And this causes adjacent channel interference, just as the harmonics in the previous one would cause interference at multiples of the fundamental. So in order to avoid the nonlinearity or distortion, as we saw in the limiter in the previous slide, to the signal, we're often operating the transmitter in a back-off area. And so we talked about the 1 dB compression point before. What we tend to do if we want to be linear is we just operate it in a region where we're below this 1 dB compression point, and that allows us to generate the least amount of harmonics. And just a comment here that you can see here in the slide is that if we do this, then most of the time we're not using the peak output power of the transmitter. And that is only a concern when you're trying to go very far distances and you're basically, if you operate at peak power, you have a lot of distortion. And the other challenge is if we operate such a system, down here, let's say, as our quiescent point, it has a lot of DC power that's able to create these higher output powers. So even though we might be down here and we're operating nice and linear, typically the system will be inefficient because it has a great deal of DC power that is necessary to be able to create high output power. So there's sort of this trade-off. I want linearity, but I want also to have low power. And so low power means we're constantly trying to move this 1 dB point back, and linearity says we're constantly trying to move it out. And so there's a trade-off there in many systems between efficiency versus linearity. And we're going to talk about that in a future module. All right, that was it. Harmonic distortion. This just comes from the products of the nonlinear transfer function, and so we get harmonics that can interfere with adjacent channels. And also spectral growth happens where if we have a broadband signal, it goes through a nonlinear system that distorts it, that broadband signal gets wider, and we can have adjacent interference to adjacent channels.